All right, so one last thing that we're going to talk about in terms of what we learn from lights. Remember, light tells us a lot of things. We talked about how we get the temperatures of stars, of your pet, anything. Just measure intensity as a function of wavelength. We recap here, right? And you measure it with all the wavelengths, and you're gonna get, something that resembles this curve. We call that the black body curve, and you identify the maximum and find the lambda max. That is the wavelength corresponding to the maximum intensity, and that gives you, from Wien's law, the temperature of that body. All right, so that was one thing. The other thing was via spectra, emission and absorption lines, you get the composition. Right now, we are going to talk about the Doppler effect, which will tell us the speed of a distant object. We're basically going to figure out whether an object that emits light is moving away from us or towards us. Here's what happens. When the source of light, so the thing that produces light, is moving relative to the receiver, that would be us, the recorded message, or what we measure about light, changes frequency or wavelength or its energy, right? Because remember, energy is h times frequency, or is h times c over wavelength. They're all related. Once you know the energy, you know the frequency, or you know the wavelength, okay? You only need one and you're gonna know the other two. Okay, here's how it works. I'm sure you have heard about trains. You probably have made it to a train station, and you probably heard a rapidly coming train, maybe like an intercity or something, coming into the station but not stopping and moving away. And it kind of sounds like this. It's kind of, the choo-choo train sound, or maybe the siren of the train, the noises that the train are very low in pitch when they are far away from you, okay? So say, right, the train is coming towards you, okay? And if it's coming towards you, the pitch becomes higher and higher and higher, right? So this is the situation. So moving towards the observer, right? What happens? You see all the wave fronts come closer together. So basically these peaks, right? Peaks of the wave are closer. So basically smaller wavelength. And I should have used blue because that looks like it's going to be a blue shift in the whatever is measured about that signal, that wave. In our case, is going to be the light wave. All right, but so this observer. Now, if it is this observer, right? So the thing is moving that way. So source of wave, and in our case, that is the light, is moving away. And so the wavelength gets longer. You see those wave fronts, right? They become further apart. If it gets longer, it's going to be redshifted. So that is all. We measure that, well, the wavelength changes, right? So measuring the shift. Who does the shift? The wavelength of emission of light. So say we have a spectrum observed in the measured in the laboratory, right? And here are some emission lines, right? So there's a certain intensity at a certain wavelength, right? So we have wavelength going that way, and the intensity is on the axis perpendicular to this page, right? So it's going to be intense whenever there is a color, and the color is given by its wavelength. Okay, so this is stationary, so velocity is 0. And then let's compare with object 1 that is moving away. What happened? You see, there was a shift. So again, I should have used red, right? So there is a shift towards longer wavelengths. That means is towards redder wavelengths, right? The red is towards the longer wavelengths. Okay, how about faster? Okay, that means the shift in wavelength is greater. So basically, the greater the shift in the wavelength is, the faster that object is moving away from us. How about the object number 3 that is moving towards us, towards the observer, that is us. What's happening? So this is the laboratory reference. You see, there was a shift that happened towards smaller wavelengths. You see how the green kind of light becomes turquoise or something, so it moves towards the blue, right? So towards moves or shifts towards the blue. So again, faster, that is greater shift. The direction of the shift tells the direction of motion. Towards us, it's going to be towards the blue, towards the shorter wavelengths. Away from us, it's going to be towards longer wavelengths or towards redder wavelengths. All right, so yeah, we measure the Doppler effects, right, from the shifts in the wavelengths of the spectral lines, and the amount of the blue shift or the red shift tells us an object's speed. And yes, there is a formula. I don't think I signed any problem in which you need the formula, but if you really need to, if I made that mistake, you can find the formula in the book. And it goes like this: lambda observed minus lambda rest or observatory, and you have divide by lambda rest is going to be the speed over the speed of light. So this is okay. So this is the amount of shift. In wavelength. All right. Now, a cautionary point. The thing is, the Doppler shift is important, but it only tells us about the part of the motion that is either towards or away from us, which it's great if the object is moving like object number 1 here. It's clearly moving away from us. For example, object number 2, there is no motion either away from the Earth, us, the observer, or towards, right? Neither. Away from us or towards us being the observer. Okay, so basically we're not going to be able to extract any information. There's not going to be no Doppler shift measured in this case. And how about situation number 3? So this is the direction of motion. It's clearly not along the line of sight. So not along the line of sight. However, we can decompose, right? You can think about decomposing this velocity into a component that is along the line of sight, right? So this is the component the line of sight, and that's going to be component perpendicular to the line of sight. And the Doppler shift, if we measure anything about this object, is only going to be about this part of motion. Okay, so that calculated from the Doppler shift. We're not going to have any information, so no info about this. All right, so that was the cautionary note. Here's an example of a problem that might appear in your exam or in the homework or tutorial for this chapter. So say we measure a line in the lab, so that is at rest at this wavelength. So this is the wavelength at rest. And now the same line in a star, the same line from the same atom or a specimen or material, right? A star has a wavelength that is, you can find it, right? So observed or moving, right, is greater than the one at rest. Okay, so what can I say about this star? I already see, because of this observation, that object, that is star, is moving along the line of sight, but because this is larger, is moving away from us. It's moving away from us. So the correct answer would be in this case